So we're going to start with the evidence that the cortex has the properties of the modular hierarchy of condition definition and detection that's predicted from the theoretical considerations. And we listed some specific predictions about the nature of this modular hierarchy, and we'll go through each of these items in turn. The first prediction is that the physical resources that detect conditions will be organized into modules, and the modules will be arranged in a hierarchy, with higher level modules made up of groups of more detailed modules. And conditions will be assigned to modules on the basis of similarity, with greater similarity in more detailed modules. In the cortex, each synapse detects a condition, and that condition is defined by the pyramidal neuron that's the source of the synapse. Each terminal branch detects conditions that are combinations of the conditions defined by its synapses. A pyramidal neuron detects conditions defined by different combinations of its terminal branch conditions. And a column detects conditions that are defined by different combinations of the conditions detected by its neurons. And within an area, each column detects conditions that are relatively similar in the sense that they're all defined within the same input space. So the cortex resources are physically organized in the way we'd expect for the predicted modular hierarchy. The second prediction about modules is that they'll define conditions heuristically from experience. And as we discussed extensively earlier in the course, there's mechanisms for adding synapses and for changing the weights of synapses, all on the basis of experience, such as the relative timing of inputs derived from experience. So there are mechanisms that support heuristic definition of conditions. The third prediction about modules is that you can expect to see much more information exchange within a module than between a module and its peer modules. In the cortex, the degree of information exchange is indicated by the degree of connectivity between structures. And we do indeed see that there's a lot more connectivity within a cortical area than between areas. There's lots of connectivity within an area, but any one area tends to exchange information with a relatively small number of other areas. Typically, there can be large information exchange with just 3 or 4 areas, and smaller degrees of exchange with up to 10%, say, of the other areas. Within an area, there's more connectivity within a cortical column than between different columns in the same area. There's a vast amount of interaction within a neuron, but between neurons, the result of all this interaction is one output carried by a single axon. A terminal branch integrates the inputs of all its synapses, but it communicates the result by a single calcium action potential. And the result of the complex chemical processes within a synapse is communicated by injection of one postsynaptic potential into a branch. So at every level, you can see there's significantly more information exchange within a module than there is between different modules on the same level. The next prediction is that modules on one level in the hierarchy will tend to be generally similar, but when you look closer, you can expect to see some differences in detail. And remember, this prediction derives from the need to construct all the modules without making too many mistakes, but ending up with modules that are specialized in different types of information processes. And if you look at different cortical areas, you can see a general similarity, an organization into about 6 layers, and the types of neurons are the same. But looking closer, you can see some detailed differences in the layering between different areas. The columns within one area have very similar layering, but when you look more closely, the numbers of neurons and the connectivity differ somewhat between columns. when you look at pyramidal neurons, they're again all generally similar, but differ somewhat in form between different layers of a column, and sometimes with larger differences between different regions. And of course, every pyramidal has a somewhat different pattern of inputs. A further prediction is that the conditions detected by different modules will tend to be orthogonal to each other, and furthermore, they won't correspond individually with behaviorally useful circumstances. And in the case of column receptive fields in the area that plays a major role in identifying visual categories, the receptive fields detected by neurons change abruptly across column boundaries, but these receptive fields don't correspond with obvious visual categories. And at the cortical area level, areas don't correspond with types of cognitive task. In fact, very similar groups of areas may be active during different types of tasks, such as this example of recalling a real event compared with imagining a future event. A further prediction is that any cognitive task will require information processes performed by many different modules. And a little earlier, we discussed the wide range of areas active during episodic memory, and at a more detailed level, if we look at the cortical area that contributes strongly to recognizing visual objects, multiple column modules support the recognition of any one object. Then there's also a prediction that in a complex learning system, the number of modules will be a compromise between resources and behavioral effectiveness. So as we looked at recently in the cortex, although some modules are shared across many different behaviors, a few modules support a specialized information process that's only needed by a relatively narrow range of behaviors, but these behaviors are critical. And there's also evidence that some different prefrontal areas tend to specialize in different general types of behaviors. And one example of this evidence is a man called Phineas Gage, who had major accidental damage to his frontal cortex. An iron bar was fired through it, but remarkably he survived. He seemed to have most of his cognitive capabilities, speech, memories, unaffected. The main change that resulted was a dramatic shift in his personality. In other words, there was a change in the types of behaviors he selected in response to his circumstances, which suggests that damage to some prefrontal areas removed the recommendation strengths in favor of certain general types of behavior, biasing his responses towards the types of behaviors recommended by the undamaged areas, and so changed his perceived personality. We also saw that because of the need for learning, information exchanges between modules must be partially ambiguous in behavioral terms. And going back to the earlier observations, we can see that the receptive field detections don't correspond with clear behaviors like object identification or category naming. And also, recall that in the striatum, the medium spiny neurons do correspond with individual behaviors, and these neurons get one or two inputs from thousands of different cortical neurons, and need to get inputs from a significant number of those cortical neurons at the same time to produce an output. So no one cortical output corresponds with a behavior. It needs some large combination of cortical outputs, and of course the combination could be different every time. The need to maintain information synchronicity in a complex learning system led to further predictions, including the need for layering rather than the reference memory that's used in electronic systems. And we see this layering very prominently in the cortex. Another prediction is that the modular hierarchy will be superimposed on the layering. And again, modules like columns can be identified on the basis of more internal connectivity than external connectivity, and in the cortex they are superimposed on the layers. Other predictions are that complex learning systems will need to define and detect conditions on a number of different levels of complexity. And in the cortex, different cortical areas get inputs from a number of other areas, and will therefore define and detect receptive fields that are combinations of the receptive fields defined by those areas. Different levels of complexity will be more effective for recommending different general types of behavior. And in some cases, areas do have an identifiable range of behavioral types that they particularly support. Not a specialization in one type of behavior, but a range of behaviors to which an area contributes more strongly. In a complex learning system, we saw that conditions need to be associated with behavioral recommendations, and at least a minimum number of condition detections is needed to get a high integrity behavior. But equally, too high a degree of condition detection would require excessive processing resources and might well confuse behavior selection. So there have to be mechanisms to limit the degree of condition detection. And in the cortex, we observe lots of inhibitory neuron populations that can regulate activity within one layer of a column, within multiple layers, or even between columns. We saw that a system, in order to develop recommendations appropriate to the presence of a group of objects, like a dog barking at a cat up a tree, will need to be able to detect conditions within each of the multiple sensory objects present, first the dog, then the cat, and then the tree, keeping them all active at the same time so that they can be combined into more complex conditions able to recommend a response to the group. The problem is that if the same resources are shared on a level that discriminates between objects, how can the condition detections be kept separate at this level so you don't perceive things like a cat with leaves or a dog with branches and so on? Providing separate physical resources for each object would require too many resources, and this led to the prediction that the processing of different sensory objects will need to be handled using the same resources shared by time division multiplexing. The processing capabilities of a condition detection resource will have to be divided up in time into periods, and each period divided up into several time slots. Then, the information from one object can be processed in the first time slot of each period, information from the second object in the second time slot, and so on. The implications are that the information processing must take place in chunks of time that are shorter than a time slot. It must be possible to perform a complete processing step, like integration of a group of spikes, within one time slot. In the cortex, an action potential spike, the indication of a condition detection, lasts for about a millisecond. And one spike injects postsynaptic potential that's mostly concentrated within a 5 to 8 millisecond window. And multiple spikes are needed to produce an effect on the target neuron, so they have to be integrated within that 5 to 8 millisecond period. We also observe that when we pay attention to objects, cortical activity is observed at a frequency of about 40 Hz. So how does all this fit together? A modulation frequency of 40 Hz has a period of 25 milliseconds. Given a postsynaptic effect that lasts 5 to 8 milliseconds, the time slots for different objects must be of that order, which leaves room for 3 or 4 time slots, 25 divided by the length of the effect. So the number of different objects we can handle simultaneously will be 3 or 4, which is just what we see in working memory. So what we've done here is to relate the capacity of working memory to the decay time of a postsynaptic potential and the gamma band frequency observed in the EEG. Another set of predictions concern the way in which changes to conditions can occur. One prediction is that receptive field changes will predominantly be expansions, and radical changes will be rare. In the cortex, for experience-based learning, synaptic weight increases, which would support expansions, appear to predominate. There's evidence that visual learning, for example, depends predominantly on synaptic weight increases. Decreases in the weights of individual synapses occur primarily if a synapse is irrelevant to the detection of a neuron receptive field. And if there's excessive detection of a receptive field, the adjustments in the cortex decrease all the synaptic weights in the same proportion, which retains a qualitatively similar receptive field and doesn't make a radical change. And the existence of the ability to accurately recognize something that's familiar implies that there's a lot of stability in the information that's recorded about experience. And the example I mentioned was that if subjects are shown thousands of photographs over a period of a couple of days, then a week later shown pairs of photographs, one seen before and the other not, they could pick out the familiar photograph with 90% accuracy. And the existence of memories for events far in the past suggests considerable long-term stability in some kind of information record. The predicted ability to add new conditions to existing sets is observed in the existence of zero-weight synapses that can be added to a dendritic branch. The prediction that receptive field expansions are triggered only by too few receptive field detections is supported by the observation that novel events are in general easier to recall in detail than routine events. And jumping ahead a little into the discussion of the hippocampus as the cortical change manager, there's much more activity in the hippocampal system during novel experiences. Then there's the prediction that the internal activity of columns will be the guiding factor determining change appropriateness. Recall that the flow of information in a column is from input layer 4 up to layers 2, 3, then down to output layers 5 and 6. So layers 2, 3 are the middle layers in terms of the flow of information. And it's indeed observed that it's the middle 2, 3 layers that provide inputs into the hippocampal system. Cortical areas provide inputs to the perirhinal and parahippocampal cortices from their middle 2, 3 layers. The perirhinal and parahippocampal cortices provide inputs from their 2, 3 layers into the entorhinal cortex. And it's the layers 2, 3 of the entorhinal cortex that provide inputs into the hippocampus proper. The final predictions relating to the cortex are that there's some functional implications that follow from the relative stability of receptive field definitions. Firstly, this stability implies that there's going to be behavioral value in indirectly activating receptive fields that aren't currently detected but have often been active in the past at the same time as currently detected fields. And this prediction is confirmed by observations that information that isn't currently present can be retrieved using currently available information. Now, recall that such indirect activations require segregation of the inputs that define direct receptor fields from the inputs that define the circumstances in which the field should be indirectly activated. And that kind of segregation is observed at the neuron level, with inputs from cortical areas closer to sensory inputs, in other words, the ones defining direct receptive fields arriving on basal dendrites, while the inputs from higher cortical areas that define when the neuron will be indirectly activated target the apical dendrite. So the structure and the properties of the cortex confirm that it's the modular hierarchy of condition definition and detection predicted to be present in any system that must learn a complex combination of behaviors with resources that aren't unlimited. So in the next section, to conclude the discussion of the cortex, we're going to have a look at the information models for the processes performed by cortical structures on different levels of detail, the information models that follow from the constraints.